Alright, today we're solving trigonometric equations with identities. If you have not already watched the solving basic trig equations from Mrs. Dennis or Mr. Rogers, I suggest you go watch those before you watch this, as this will be a little bit more complicated. For today, all of our solutions are going to be restricted from between 0 and 2 pi. That is so we have a specific range in which we're giving our solutions. We're not providing a general solution, we have a specific solution. And we have 3 example problems we're going to work through. All this is basically going to be applying identities, the verifying and simplifying identities that we've done in the past to solving equations. So let's go on over and work through the first problem. So here's the first example that I had. Tangent squared theta equals 1 minus secant theta. And your first step with this, when you're solving with identities, is you need to realize that in general you're going to do this every time you have multiple trig functions, like if you have sine and cosine, sine and secant, or something like that. The exception to that is if you can factor something out and get, using the zero product properties, be able to set both different trig functions equal to 0 individually, then you can just do that. However, in the case examples I'll be doing, we'll need to use some trig identities. So the first thing we need to do is, how can we get tangent or secant to be the same thing? Well, I see tangent squared, and I know from my trig identity sheet that tangent squared is secant squared minus 1. So I'm going to replace tangent squared with secant squared minus 1. And now this is all in terms of secant or some number. Now I'm going to rearrange, moving everything to the left side. So here we have our rearranged function. We have a secant squared theta plus secant theta minus 2 equals 0. Now, you may notice at this point that this is in the form of a quadratic. And so we could write it like this: u squared plus u minus 2, where u equals secant theta. And you don't have to do this, but for some people this helps them to recognize that they can factor this. So we could factor this to u minus 1 and u plus 2 equals 0. So let's just rewrite this with our secant, replace the u again with secant. So we have secant theta minus 1 times secant theta plus 2 equals 0. Now we can use our zero product property because we have a combination of 2 things being multiplied together. And we can write this as 2 separate equations. So secant of theta equals 1 and secant of theta equals negative 2. All of our solutions today will be from the unit circle. So if all of our solutions are from the unit circle, we don't have, you could write them, but we haven't written secant or cosecant or cotangent. So let's just revision this as cosine. So we're just going to take the reciprocal of both sides. So the reciprocal of secant is cosine, the reciprocal of 1 is 1. And over here, we have cosine and negative 1/2. So we'll just do that. And then all that's left is to look at our unit circle, or hopefully you've memorized it, and look at where the solutions from 0 to 2 pi are for cosine equals 1 and cosine equals negative 1/2. So if we look over here, cosine equals 1 at 0, and cosine equals negative 1/2 at 4 pi thirds and negative 4 pi thirds. And so that's our answer. Theta equals 0, 4 pi thirds, and 5 pi thirds. If you need to re-go over that, or if you have any questions, please let me know. But this is a relatively straightforward application of how this works. Now let's look at our next example. Sine squared of x minus 3 cosine squared x equals negative 2. So once again, we want everything in terms of sine and cosine. There's several ways we can do this. What I'm going to do is I'm going to take this sine squared x and rewrite it in terms of the Pythagorean identity, and sine squared x equals 1 minus cosine squared x. So if I do that, then all this is now in terms of cosine and some number, which this is fine. Now we're going to combine like terms and rearrange. So negative cosine minus negative 3 cosine is negative 4 cosine. We can move the 1 over, and that gets us negative 3. So negative 4 cosine squared x equals negative 3. Then we divide the negative 4 over. So we have cosine squared x equals 3/4. The way to get rid of a squared is to take a square root. So we'll take the square root. Square root of 3 is the square root of 3, and square root of 4 is 2. We took a square root, so we have plus or minus. So don't forget, this is an area that lots of people forget. We do have a plus or minus square root of 3 over 2. And now we just have to go to our unit circle, and where is cosine of x equal to plus or minus square root of 3 over 2? Well, cosine of x is equal to square root of 3 over 2 at pi 6, negative square root of 3 over 2 at 5 pi 6, negative square root of 3 over 2 also at 7 pi over 6, and at 11 pi over 6. And so those are our answers. So x equals those values. Now I'm going to do a slightly odder example. Here we have cosine x plus 1 equals sine x. This seems simpler than all the others. However, no matter how we rearrange this right now, there's no real trig identity that's obvious that turns this into cosine into sine or sine to cosine. Like, there's not real anything obvious and straightforward that gets us to a nice trig identity. So to fix that, what we're going to do is we're going to square both sides. And that looks like that. So the cosine x plus 1 quantity squared and sine squared x. Now we're going to distribute out here. So we get cosine squared x plus 2 cosine x plus 1. Don't forget your middle term. Too many people turn this into cosine squared x plus 1. The 2 cosine x is part of this. If it helps, write this out as cosine x plus 1 times cosine x plus 1 and FOIL. And it may help to avoid missing this, but this is fairly critical. Now that we've got all this in cosine, you'll notice we have sine squared x, and we happen to be able to put this in terms of cosine as well. This is 1 minus cosine squared x. Now, just because all my examples wind up in terms of cosine does not mean they have to. Technically, this one ended in secant. But just keep in mind that the end goal is not necessarily to get this in terms of cosine. We could have done this another way. This is just the way that seemed easiest. Like this one, we could have put things in terms of sine, and it would have worked out just fine. So, back to this. We have cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. So we're going to move everything to the left side. So we're going to add cosine squared x and subtract 1. And that gives us 2 cosine squared x plus 2 cosine x equals 0. And now the easy way to move forward from here is we have 2 cosine x in common between both of these. So we can factor out 2 cosine x. And that gives us this. And I'll just take a moment and just say that if this was like, if for some reason this was sine x plus 1, we could still solve from here because we can use the zero product property to say 2 cosine x equals 0 and sine x equals, sine x plus 1 equals 0. And we can still solve both of those. So just keep in mind that if you can get to the terms of zero product property, even if you have 2 different trig functions, that's not an issue. Anyway, so we'll use the zero product property with these. So 2 cosine x equals 0 and cosine x equals negative 1. So cosine x equals 0 and cosine x equals -1. So it would seem that our solutions are, if we look at our unit circle for cosine x equals 0 or -1, it's 0 at pi halves, and it's -1, or it's 0 at pi halves and 3 pi halves, and it's -1 at pi. So those are our solutions based on this equation. However, we need to remember that we basically doubled the number of solutions by squaring everything. So it's possible, because we took this step of squaring everything, that here we may have extraneous solutions. So we need to consider that. And the way you deal with that is we take each of these solutions and plug them into the original equation, cosine x plus 1 equals sine x. Well, if we plug pi halves in here, cosine of pi halves is 0, so 0 plus 1 is 1, and sine of pi halves is 1, so 1 equals 1. So pi halves is a valid solution. Well, let's plug in pi. Well, cosine of pi is -1, -1 plus 1 is 0, and sine of pi is 0, so 0 equals 0, so pi is still a valid solution. And let's plug in 3 pi halves. Cosine of 3 pi halves is 0, 0 plus 1 is 1, and sine of 3 pi halves is -1. So now we have the case where 1 equals -1, which is not true. So our actual solutions are just pi halves and pi. So that concludes my 3 example problems that I wanted to work through. These are relatively complex compared to the work I'm going to ask you to work through. So these are some of the harder end questions. If you have questions on any of the problems, be sure to ask me. I am available on Schoology. But that concludes our lesson for the day.